All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. I don't know. For some reason, my audio just sounds off to me. You guys are hearing me okay?
Yeah, we can hear you.
Like at usual levels?
Yeah.
Okay. For some reason, it just sounds weird to me today. Okay, all right. Let's jump into it. Okay, there we go. So this is what we were doing yesterday. Make sure I can see the chat here. We started an example of a basketball player taking shots, free throws, and we wanted to find the probability that he made a certain number of shots, or at least a certain number of shots, or between a certain number of shots. And we figured out that there's a nice little formula that would describe the situation. It's called the binomial probability formula. And this is a formula that we do when we're repeating an experiment, which is assumed to be you're doing the identical thing over and over and over n times. And each time is independent of the other. And there are only two possible outcomes, which you describe as success or failure. And success or failure can be very broad. Success is just the thing you're looking for to happen, right? It might be a bad thing, it doesn't matter. But success just is, it's the thing you care about happening. That's what you call a success. In this case, we wanted to know how many free throws he made. Therefore, him making a shot was success. If we wanted to find probabilities of how many free throws he would lose, then him missing a shot would be a success. I just want you to get that. But you have these individual experiments. They're all independent of each other, but they're identical otherwise. And if they only have two possible outcomes, it turns out that you can find the probability of a certain number of outcomes going the way you want by this formula. Once you set the probability of your success to be P and the probability of your failure to be Q, which is of course equal to 1 minus P, then the number, if you want to find the probability that there are K successes, this is going to be the formula. And we went through that with this example. So what is the probability that he has 10 successes? Well, it's just x equals 10 in that formula. That was 2.8%. What is the probability that he makes exactly 2 successes, makes exactly 2 free throws? That's 0.14%. What is the probability that he'll make between 3 and 5? That's about 14% using that formula, where we break up between 3 and 5 into 3 separate instances that of course don't overlap, because if he made 3, then he would not have made 4 or 5. So they're mutually exclusive, and we can add the probabilities. Probability that he will make greater than 1, that was actually pretty high. That's 99.9994%, which, I mean, this is a guy who makes 70% of the shots that he takes, right? So out of 10, you expect roughly that he will make around 7. So the chances that he's going to get greater than 1 are pretty high, right? You can kind of almost count on it, right? And I left you with another example to try this same thing. And that's how we're going to start off today. Okay, some of these problems here are coming from problem set 3, which I'll paste here in the notes on a separate page. We're going to do problem 16 now from this set. Later, I'm also going to do like problems 10 and 11, I think. But moving on to today. So we're assuming there are 4 blood types, O, A, B, and AB, and they occur in the population with these frequencies. You can think of those as the probability that someone will have a certain blood type. So there's a 43% chance that someone has blood type O, 41% chance that someone has blood type A, 11% chance that someone have a B blood type, and 0.05, there's a 5% chance that someone will have AB blood type. Okay. There are also things that are called RH factors. These are protein factors in your blood. People usually have one of two, not both, right? They have like RH plus and RH minus, and they vary by 86% for the positive and 14% for the negative. So you can be an A positive or something like that, or you can be an A negative or a B minus or an O positive or whatever, right? So you can have the blood type with a positive or negative attached to it, which describes a certain blood protein that you have. Okay. Also, we have a chart here that tells you who could donate blood to who and who could receive blood from who. So for example, if you have an A positive blood type, then you can donate blood to someone who has an A positive or an AB positive blood type. So when you go to the blood donor, you want to go to be a blood donor, you have A positive, your blood would help someone who's of A positive or AB positive. You yourself, as an A positive blood type person, would be able to receive blood from an A positive, an A negative, an O positive, or an O negative, right? So that's what these charts are saying. So for all the blood types, it basically tells you who can you donate blood to, who can you receive blood from. Okay, so now we're going to go into some questions here. What is the probability that what is the probability that a random person can donate blood to a person that has blood type A with an RH plus, right? So we can pretend that someone comes into a clinic or something, they need blood. We find that they are A positive, and for whatever reason, let's say we don't have blood to give to this person. But then a random blood donor just walks in the door right there. Wow, that's just in the nick of time. What is the probability that that random blood donor could donate blood to the A positive person? That's what we want to know. So let's do that. So A. So we want the probability random donor can donate to A positive, right? Call this event D, probability of donate, right? So this, of course, is going to be equal to what? This is basically asking, well, who can donate blood to an A positive? Well, they can receive blood from an A positive or an A negative or an O positive or an O negative. So this means the probability that the random donor is A positive or A negative or O positive or O negative, right? Now, you can't have someone who has two different blood types, so these are all mutually exclusive. And by the way, blood type A splits into two different blood types, positive and negative. So if you're looking for someone who's A positive or A negative, you can actually just think of that as you're looking for someone who's blood type A. You need a type A person. And then these two would comprise of a type O person. Okay, so this is pretty much the probability of a random donor being A or O. And these are mutually exclusive. So what we can say then is, so this means the probability of D is just going to be the probability that someone is of blood type A plus the probability that someone is of blood type O. And so that's going to be 0.41 plus type O was 0.43. So, I mean, far from certain, but there's actually a good chance, right? Like if you're A positive and you walk into a blood bank, you need blood, like, or you walk into a clinic and you need blood, there's an 84% chance that any random person would be able to donate blood to you, which is it's great. I think there are some that it's not so great. AB positive, they're awesome. Anyone can donate to them. Like if you have blood, I'll take it, right? O negative can donate blood to everyone, right? So that's just some stats there. And I believe these are actually true. Like I didn't just randomly make these up. I actually looked up this chart. I think, I'm not going to vouch for the source, but anyway, yeah, 84% chance. Let's go on to B. All right. A hospital needs 5 units of blood to give to a patient having blood type A positive, right? So we have the same A positive person. Now we're going to pretend that 8 people enter into the a blood donation center that can feed into this hospital. And each person gives 1 unit of blood, right? You can't take too much blood from somebody because, you know, kind of affect their health. What is the probability that these 3 things will happen? At least 1 unit of blood can be found for the patient. The hospital will be able to attain all the blood that it needs for the patient, or the hospital will obtain exactly the amount of blood that it needs for the patient. Now, at first, this might seem very daunting to figure out, but then if you start to look at it in the lens of what we started yesterday, you'll realize that, okay, so if these 8 random people walk into the hospital, and I want to know if they can donate to this patient, well, that's just a yes or no question, isn't it? Right? So you check the first person, do they have a blood type that can donate to this person? Yes or no, right? If yes, success, we have another unit of blood that we need. If no, failure, we need some other unit of blood. You text the second person, can they donate to the person? Yes or no. Test the third person, can they donate to the person? Yes or no, right? And you go through successively. What you'll notice is that in part B, you're actually setting up independent trials. Like random people walk into a blood bank, there's no reason to expect that their blood type would affect each other. They're not related. You don't know anything. They're just random people, right? So you have independent trials. You're doing the same thing. You're drawing blood and see if they can be donated to a certain patient. And you have 2 possible outcomes. Either they can donate or they can't, right? Turns out this is a binomial situation. Here are n equals 8. 8 people walk into the blood bank. We are going to do this experiment 8 times, right? Now we found the probability that a random person can donate to an A positive. So we know that P is equal to, there's an 84% chance. This is from part A. So the probability of having a success with a random person is 84%. This, of course, means that the probability of failure, right, is going to be 36%. Not 36, 16. 16%, right? That's just 1 minus P. Okay, so this is a binomial, right? So repeating the experiment of seeing if a donor can donate to our patient. And for us, the possible outcomes per test is there are only two. Either yes, they can, this is our success, or no, they can't, this is our failure, right? And these don't depend on each other. So now once you actually realize that this problem is binomial, because these three things that I mentioned last time, these three situations, now that you know about binomials, these three situations, it's going to be something that you're always going to be looking for. The problem that I'm looking at, are these three things satisfied? Repeating the same experiment, each time it's independent, and there are only two possible outcomes per experiment. Then you can think of it as binomial. So now we can do that. So probably at least one can be found. So what I'll do here is let X be the number of successes. Right, which is 1 unit per person. So now if we have 1, what we want here, we want the probability that your X is greater than or equal to 1, right? At least 1 unit can be found. Now, of course, probability that X is greater than or equal to 1 is the probability that X equals 1 plus probability that X equals 2 plus probability that X equals 8. All 8 people can donate. Now that's a lot of things to go through for our formula. So I would actually use the complement. This is just 1 minus the probability that no one can donate, right? No one donating is the opposite of at least one donating. So this is a complement. Now we can just plug into the formula. This is 8 choose 0, P to the 0, Q to the n minus 0. Of course, that's just going to be 0.16 to the 8, which means you just have 8 failures in a row, and they're all independent. So you kind of just multiply the probabilities. Sorry, 1 minus that. So at least one, there's a good chance. There's roughly a 99.99% chance that you're going to get the blood that you need here. If you actually plug that into your calculator. Which is completely reasonable. I mean, there was an 84% chance that a random person can donate blood. So if you have 8 random people walking in, each of them having an 84% chance of being able to donate blood to this person, the chances are pretty high that they're going to get at least 1 unit of blood. So yeah, that's 1 unit of blood. Now we go to 2. And I want you to be very careful of the wording here. In fact, the wording of the problem tells you to be careful. Right? What is the probability that the hospital will be able to attain all the blood that it needs? And be careful that to consider all possibilities. We know that they need 5 for this person. But just saying that they'll get exactly 5 isn't quite the right thing, because if they got 6, they would also have enough for this person. If they got 7, they would also have enough for this person. If they got 8, they would also have enough for this person. There are more than one ways to actually get all the blood that they need. They can get all the blood that they need and more. So what part B is talking about, or part B, part 2 is talking about, we want the probability that the number of people who can donate is at least 5. That way we'll get all the blood that we need. We might even get extra, right? So that's what it meant by be careful about all possibilities. Now, of course, probability of x greater than or equal to 5. This is probability that x equals 5 plus probability that x equals 6 plus probability that x equals 8. And you can just do this directly. So, I mean, there's only one. I don't know why I put ellipses for just one of these guys. Probably that x equals 7 plus the probability that x equals 8. So this is going to be 8. Choose the 5 people who can donate. The probability that they're able to donate is 0.84. Probably that they're not able to donate is 0.16. Here, 8 choose 6. Probably that they're able to donate. Probably that they're not able to donate. Eight choose 7. Probably that they're able to donate. Probably that they're not able to donate. 8 choose 8. Probably that they're able to donate. Probably that they're not able to donate. So 0. And you can plug this in and you would get, I think, write it in percentage. There's a 97.3% chance that they'll get the blood that they need. Okay. So good news for the A positive person. The hospital will attain exactly the blood that it needs and no more. Well, this just means they get exactly 5 units. So if we look at part 3, we want probability that they get 5. Now, probability that x equals 5, well, that's just going to be 8 choose 5, 0.84 to the 5, 0.16 to the 8 minus 5. Probably of getting exactly 5 and no more, no less, that's around 9%. Okay. Yeah, that's this problem. Part B was binomial. And it's a kind of situation that you know about now, and you're just going to look out for it. That's how it's going to go. The x in our binomial formula brings up an important notion. Now, I'm going to tell you what this notion is, and pretty much we're going to move on. So somehow it's in the syllabus that I'm supposed to tell you about this thing, but we're not actually going to be able to use it very much or very well. So, or not use it as much as the reason why the concept was invented. So the invention of this concept is really to allow us to use what we know about functions and calculus and all this other fancy math that we know in probability. And so what we do need to define is some sort of variable in probability that we can treat as a function to do stuff with it. And that actually opens up a whole new world of probability and statistics, believe it or not. And yeah, it's not something that we're going to touch on at all. We're doing finite probability. And for this kind of notion would lead you into continuous probability. So I'm just kind of going to tell you what it is, kind of describe what it is, and then we can move on. So this is the idea of random variables. So definition, a random variable is a function, right? So now we're going to want to be able to somehow connect probability to the output of some function. So whose domain is the sample space, say a sample space, i.e. its inputs are sample points. And its range is a subset of the real numbers. So you input a sample point and it outputs a number. So i.e. a random variable which we usually call them uppercase letters, a random variable x assigns a numerical value to each possible outcome. Right? For example, what we did with the binomial thing is called a random, it was a random variable. This x here that counts the number of people. What you will notice that the x is describing, it's actually describing an event. When I say x outputs a value of greater than or equal to 1, I'm actually describing an event that greater than or equal to 1 people can donate, right? Like I'm using the number in place of a sentence or an event that I care about, right? And so when I ask about what is the probability that they'll get all the blood they need, maybe even more, that is an event. For us, what that event means is that the output of our function is 5, 6, 7, or 8, right? So it kind of takes you from like a real world scenario to a very numerical scenario where you're now working with a function. And you can use this function in various ways. If the function behaves a certain kind of way, you can do very sophisticated things with this function, like calculus. And that actually leads you to many more probability techniques. So, example, you flip a coin, okay? Let x equals, I want to flip a coin twice. Let x equals the number of heads obtained. Then x is a random variable. Notice that it went from some event happening, heads, to giving you a number. So when you look at the sample space, we know all the possibilities for this. It's like you can get heads and heads, or you can get heads then tails, or you can get tails then heads, or you can get tails then tails. What our X does is our X outputs, well, one of three numbers, right? It will, if this is the event that occurs, it will output the number 2, right? If this is the event that occurs, it will output the number 1. If this is the event that occurs, it'll output the number 1. And if this is the event that occurs, it will output the number 0. So X is a function. All its possible outputs are 0, 1, or 2. And what these numbers actually represent, when you see the number 0, you know that means no heads. If you see the number 1, that means you either got a heads then a tails, or a tails then a heads. If you see the number 2, it means you got heads and heads, right? You got 2 heads. You can actually use the numbers to talk about the events, right? Which is actually super useful when it comes to mathematics. So another example, if X is the number of successes of a binomial type experiment where the probability of X equals K is N choose K, P to the K, Q to the N minus K, then X is a binomial random variable. Right? And its possible outputs would be anything from 0 up to N going by integers. Right? So that's what a random variable is. And I'm pretty much not going to say anything other than that. So what I want to do now is maybe talk about, see my notes here, probability distributions. So moving on. We're finally getting to the title. Today we're supposed to talk about probability distributions and expected value. Okay. Let's give a definition here. A probability distribution is for us a table. Really, you can think of it as a function as well. That basically connects the output of a random variable to some probability. For us, it's a table. Oh, I'm messing up on my mouse. Which lists all possible outcomes. And the probability of each outcome. I want you to think of it as a table because whenever I ask for it, I would expect you to give me the answer as a table, but it's really a function. The inputs are the values of a random variable. Outputs are probabilities. So these look like you're going to have a table with 2 rows, pretty much. You're going to have x. So this is some random variable here. So remember, the random variable describes possible outcomes, but it describes them as numbers. So it'll have a bunch of numbers that you can put here. So let's say output can be x1 or x2 or x3. xn minus 1, xn. So it has n possibilities. And then down here, you put what is the probability that x equals that value, right? So this you can think of as P1, P2, P3, Pn minus 1, Pn. And what this really is, this is the probability that your x would be equal to x1. This would be the probability that your x will equal x2, etc. Right? So that's a probability distribution where you just tell me all possible outcomes and you can tell me what's their probability. So for example, what is the probability distribution of a fair coin flip, right? That means your x, you kind of think of it as heads or tails, and you may assign numerical values. Right? So you can decide, okay, if it's heads, the output is 0. And if it's tails, the output is 1. And then what you do now is you find what is the probability of x. And for this, you would put a half and a half, because you know there's a half probability. That is a probability distribution. This table is a probability distribution. We can also do an example. Probability distribution of rolling a 6-sided die, right? So if I let x be the output of the 6-sided die, so x, so here my x has 6 possible values, could be a 1 or a 2 or a 3 or a 4 or a 5 or a 6, right? And probability of that value, well, there's a 1/6 chance, 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 a 1/6 chance. Right? That's a probability distribution. So if I ask you, what is the probability distribution of rolling a 6-sided die? That's it. So I'm just going back over some problems that we've looked at before and just kind of having you reinterpret them in terms of probability distributions. Here's something else we had, probability distribution of the sum of two rolled six-sided dice, right? So we know the possible values for that. The sum could be 2 if I get 2 ones, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12 if I got 2 sixes. And what is the probability of getting these values? Well, we also saw that this was 1 out of 36, 2 out of 36, 3 out of 36, 4 out of 36, 5 out of 36, 6 out of 36. And we know that 7 was the most likely, and it starts counting down the ladder after that. 5 out of 36, 4 out of 36, 3 out of 36, 2 out of 36, 1 out of 36. Right? I can talk about something called a binomial distribution. And basically what that guy is, that's just, so here's my x. X can be 0, can be 1, can be 2, can be some random value k, and it can go all the way up to some number n. Probability of x. What's the probability of 0? Well, it's n choose 0, p to the 0, q to the n. Probability of getting a 1 is n choose 1, p to the 1, q to the n minus 1. Probability of n here is n choose 2, p to the 2, q to the n minus 2. Here, the probability is n choose k, p to the k, q to the n minus k. Here, the probability is n choose n, p to the n, q to the 0, right? So for a given binomial situation, I can create this table of all these values. Now, probability distributions are very important in general. But for us, they are important in finding expected value or the mean of something. So given a distribution P1, P2, P3, Pn, we define the expected value of x to be, this is the symbol, E of x. Sometimes you use a Greek letter mu, mu of x. And that is just the product of the outcome times its probability, and you add them all up. It's a sum product. So this is x1 times p1 plus x2 times p2 plus x3 times p3 plus dot, 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 xn times pn. Right. This can also be written as the sum I goes from 1 up to n of xi times pi, but you don't really have to know that notation, just know that this is what it is. Multiply the outcome times its probability and multiply each outcome times its probability and add them all together, right? And this is what we call the expected value or the mean. Right, so you can do that. We have x can be 1, 2, 3, 4, 5, 6. This is 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6. This means the expected value is just going to be 1 times 1, 6, plus 2 times 1, 6, plus 3 times 1, 6, all the way to 6 times 1, 6. So it's going to be 1, 6 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. It's going to be 1, 6 over 6 times 7 over 2. So you'll get 7 halves, or 3.5. Right? Now for the roll of a die, that number, okay, what do you expect if I'm going to roll a die? You'll get a 3.5. What does that even mean? Doesn't even make any sense, really. But you'll see in other examples, this number is actually going to be very important. But we'll pick up with that next time with going through these 2 small examples, and you'll see why this is useful. Try these. So you go into a casino and you have a game. Expected value can tell you how much you should expect to win or lose from that game. Now, of course, if you walk into a casino, the expected value is always negative. The house always wins eventually. But you can try these. Expected value really tells you, where do I expect to end up if I were to do this thing over and over and over again? That's basically the idea. And if you were to roll a dice over and over and over again and find the average of all the numbers that you get each time, the average is going to get closer and closer to 3.5. That's what that 3.5 represents. The average in the sense that you guys think about it, right? Average is the sum of all the numbers divided by the number of numbers there are. The expected value actually gets you close to that number in a probabilistic environment, which is good to know. You want to know how something will perform on average when there are only probabilities. You don't know for sure what's going to happen. But you want to know, on average, if this were to happen a lot, like where would we be? You know, like that's what this actually answers. But try those 2 for next time and we'll see that. So next time we'll do those, and I think that would finish probability. After that, we're going to move on to some statistics. So we're only going to do the very basics of statistics. We're going to look at some important graphs for statistics. We are going to look at measures of central tendency, like the mean, the average, the mode, the median, measures of spread, like variance, standard deviation, things of that sort. Maybe if we have time, I'll do like box plots for you guys and stuff like that, but that probably won't be until next week, Wednesday or something. Okay, we will stop there for now. Thank you for your time and attention. Already over time, so let's get out of here. I will see you guys in the next one. Ciao.